In December 2025, astronomers confirmed that comet 3I Atlas had completed its closest approach to Earth and the Sun and is now leaving the solar system for good. This object is only the third known visitor ever observed coming from interstellar space, offering scientists a rare opportunity to study material that formed around another star. During its passage, 3I Atlas behaved largely like a normal comet, but with notable exceptions. As it approached the Sun, it brightened far more rapidly than expected, raising new scientific questions about its composition and origin. Now, as the comet heads back into interstellar space, researchers are shifting their focus from tracking its motion to understanding what it revealed about planetary systems beyond our own. In this video, we will explore how 3I Atlas was discovered, why it is scientifically important, and what its brief visit means for future research. Let's get started. The story of Comet 3I Atlas begins not with spectacle, but with routine observation. On July 1, 2025, automated survey telescopes detected a fast-moving object whose motion did not immediately resemble that of a typical asteroid or comet. At first, it appeared unremarkable, but as astronomers refined its orbit, a key detail emerged. The object was not gravitationally bound to the Sun. Its trajectory was strongly hyperbolic, meaning it was moving too fast and along a path that could not be explained by the solar system's gravity. This placed it in an exceptionally rare category, an interstellar object passing through our system without originating from it. The designation 3I Atlas followed, marking it as only the third confirmed interstellar visitor ever detected, after Oumuamua in 2017 and 2I Borisov in 2019. Unlike Oumuamua, which showed little to no cometary activity, 3I Atlas quickly displayed clear signs of being an active comet. As it approached the Sun, solar heating triggered the release of gas and dust from its nucleus, forming a visible coma and a faint tail. This confirmed that the object contained volatile ices and behaved broadly in line with known comet physics. Once its interstellar nature was confirmed, observatories worldwide redirected their attention toward it. Astronomers reconstructed its incoming trajectory and found that it entered the solar system from a direction inconsistent with nearby stellar populations. This supported the conclusion that 3I Atlas originated elsewhere in the Milky Way. The comet reached perihelion, its closest point to the Sun, in late October 2025. On December 19th, it made its closest approach to Earth, passing at a distance of roughly 270 million kilometers. While this distance posed no concern, it represented the peak opportunity for detailed observation before the comet began fading and accelerating outward. At that point, the discovery phase ended. What followed was a transition from detection to interpretation. The significance of 3I Atlas lies in its origin rather than its proximity. This comet did not form alongside the Sun. It is a fragment of another planetary system shaped by conditions that may differ substantially from those that govern the early solar system. Spectroscopic observations revealed that 3I Atlas is rich in water ice, dust, and volatile compounds. In broad terms, its composition resembles that of long-period comets from our own Oort cloud. This similarity is scientifically important. It suggests that the fundamental ingredients required to form comets may be common across the galaxy, even if their environments of origin vary. One of the most intriguing conclusions comes from orbital modeling rather than direct measurement. When researchers traced the comet's path backward through space, its velocity and direction were consistent with an origin in the Milky Way's thick disk, a population of stars that formed earlier than the region where the Sun resides. If this interpretation is correct, 3I Atlas could be significantly older than the solar system itself, possibly approaching 7 billion years in age. That would make it the oldest comet ever observed. Age alone, however, does not explain the comet's most surprising behavior. As 3I Atlas approached the Sun, it brightened much more rapidly than existing models predicted. This increase in brightness exceeded what astronomers typically observe in Oort cloud comets at comparable distances. The cause of this rapid brightening remains uncertain. One possibility is that the comet contains unusually volatile ices that sublimate efficiently even under modest heating. Another is that structural changes, such as surface fragmentation or exposure of fresh material, played a role. At present, no single explanation fully accounts for the observations. Importantly, there is no evidence suggesting that 3I Atlas requires exotic physics or non-natural explanations. Its behavior fits within the broad framework of cometary science, even if it challenges some assumptions. This distinguishes it from earlier interstellar objects, where limited data fueled wider speculation. In this way, 3I Atlas acts as a comparative sample. It allows scientists to test whether the processes that shape comets in our solar system are universal, or whether they vary significantly depending on where and when a comet forms. Although 3I Atlas is now leaving the inner solar system, its scientific relevance is only beginning to unfold. Observations collected during its passage span multiple wavelengths, including visible light, infrared emissions, and X-ray signals produced by interactions between the comet's coma and the solar wind. These datasets will be analyzed for years to come. One immediate implication concerns detection capability. Compared to earlier interstellar objects, 3I Atlas was identified relatively early in its approach. This allowed coordinated observation campaigns across multiple instruments and institutions. The improvement reflects advances in sky surveys, data processing, and orbital modeling. These advances suggest that interstellar objects may be more common than previously assumed. The limiting factor has likely been detection rather than rarity. As survey coverage improves further, astronomers expect to identify more such objects, possibly at much greater distances and earlier stages of their approach. Future observatories, particularly wide-field survey telescopes, are expected to accelerate this trend. Earlier detection could eventually make spacecraft interception feasible, allowing direct sampling of interstellar material. While no such mission could realistically target 3I Atlas, due to its speed and trajectory, its passage strengthens the case for developing rapid response capabilities. There are also broader implications for planetary science. Interstellar comets demonstrate that material is exchanged between star systems over galactic timescales. This raises important questions about how often water, organic compounds, and other materials are transported between planetary systems. It also reframes discussions about the early delivery of key ingredients to planets, including Earth. As 3I Atlas continues outward and fades from view, it becomes inaccessible once again. What remains are the observations, spectra, light curves, and orbital reconstructions that preserve its scientific value long after the object itself is gone. Comet 3I Atlas has completed its passage through the solar system and is now returning to interstellar space. Its observations confirm that material from other star systems naturally passes through our own. The data it left behind will continue shaping our understanding of planetary systems beyond the Sun.